There is a star in the sky tonight that should not exist. Not in the way black holes shouldn't exist, or the way dark matter shouldn't exist. Those things are strange, yes, but they fit inside the story we've built. They belong to this universe. They were born here. They will end here. This star is different. This star, when we measured it, came back older than everything. Older than the galaxies. Older than the first light. Older, according to some of our best measurements, than the universe itself. And for a moment, a long, uncomfortable, career-defining moment for a number of very serious scientists, that result just sat there, on paper, in peer-reviewed journals, staring back at everyone who looked at it. A star. 14.46 billion years old. A universe. 13.8 billion years old. You don't need a physics degree to see the problem. It's like finding a photograph of someone's grandfather that was taken before their grandmother was born. It shouldn't be possible, and yet there it is. Crisp. Documented. Seemingly real. The star has a name. 2 names, actually. A catalogue name, HD140283, which tells you nothing and sounds like a password no one chose. And a nickname, given to it by the people who study it, who apparently had a sense of occasion. Methuselah, name for the oldest man in the Bible, a man said to have lived 969 years, a man whose name became a word for something impossibly, almost insultingly old. They gave that name to a star, and then they measured it, and the number they got back broke something in cosmology. Just a little, just enough to make everyone stop and ask a question we don't entirely know how to answer. What do you do when a star is older than the universe? Let's begin somewhere simple, somewhere almost everyone has stood at least once, outside at night, looking up and wondering. We've been doing this for as long as we've been human. Longer, probably. Some version of our ancestors stood on some version of this ground and watched the stars come out and felt something they couldn't name. Or, maybe, or fear, or the first stirrings of curiosity, that particular itch in the mind that says, what is that? And more importantly, why? For most of human history, the stars were permanent, fixed. They moved across the sky in predictable arcs because the sky itself was turning, but the stars themselves didn't change. They were eternal, or close enough to eternal that no human life was long enough to see otherwise. That belief held for thousands of years. The stars were ancient, yes, but ancient in the way stone is ancient, in the way mountains are ancient. Present at the beginning, present now, present at the end, the ancient Greeks imagined them pinned to a vast crystalline sphere rotating overhead. Later civilizations mapped them, named them, built temples aligned to their rising and setting. Every culture on Earth, without exception, looked up and tried to make sense of what was there. None of them imagined the stars were anything other than permanent fixtures. Why would they? On the timescale of a human life, even a long one, even a dynasty, even a civilization, the stars didn't change. Constellations that appeared in the sky above the builders of Stonehenge are the same constellations that appear above you tonight. The same patterns, the same apparent positions, the same cold, steady light. The sky felt like a ceiling. Decorated, yes. Beautiful, certainly. But fixed, unchanging. A guarantee that some things, at least, would endure. Then we started actually looking, really looking, with mathematics, with telescopes, with spectroscopes and photographic plates, and eventually with instruments we launched into space on columns of fire. And the ceiling dissolved, and the stars stopped being fixtures and became something else entirely. Objects, places, objects with properties that could be measured and understood. Places that were born and aged and died in cycles stretching across billions of years. The shift was not sudden. It happened slowly, over centuries. Galileo turned a telescope skyward and found that the moon had mountains, that Jupiter had moons of its own, that Venus had phases like our moon. all of it inconsistent with the simple picture of eternal, perfect celestial spheres. Newton worked out the mathematics of gravity and showed that the same force pulling an apple from a tree was guiding the planets in their orbits. Halley recognised that a bright comet recorded in 1531 and in 1607 and in 1682 was the same object returning again and again on a predictable path. The cosmos was not a painting, it had rules, it had history. Then in the early 20th century everything accelerated. Edwin Hubble showed that the fuzzy patches of light called nebulae, long assumed to be clouds within our own galaxy, were in fact entire separate galaxies, each containing hundreds of billions of stars, each impossibly far away. The Milky Way was not the universe. It was one island in an ocean of galaxies stretching to distances the mind refused to hold. And those galaxies were moving, not randomly but systematically, all of them racing away from each other, the universe itself expanding in every direction at once, running the expansion backward like a film in reverse. Everything converged to a single point at a finite moment in the past. The universe had a beginning, and if it had a beginning, it had an age, and if it had an age, then the stars inside it, all of them, including the ancient dim one in Libra, were younger than that age, had to be, logically, necessarily, didn't they? Objects, places, objects with properties that could be measured, places that were born and aged and died, and everything changed. The first thing we discovered, the first real shock, was that the stars are not all the same. They come in different colours, different sizes, different temperatures. Some burn blue-white with a ferocity that would incinerate anything we could imagine. Others glow red and dim, cold by stellar standards so enormous that if you placed them at the centre of our solar system, they would swallow Jupiter whole. Our own sun sits somewhere in the middle. Ordinary, average, almost boring. Yellow-white, medium-sized, neither the hottest nor the coolest thing in the sky. One of perhaps 200 billion stars in the Milky Way alone. A grain of sand on an endless beach. The second thing we discovered was that the stars are not eternal. They are born, they live, they die. The universe is not a static painting. It is a story. A long, slow, violent, beautiful story told in fire and gravity and light. Stars are characters in that story. Some live for billions of years, some burn out in a few million. All of them eventually end, and if they end, they must have begun. And if they began, then theoretically you can figure out when. This is where stellar age dating comes in. And this is where the story of Methuselah really starts. How old is a star? It sounds like the kind of question a child asks on a long car ride. Innocent, curious, easy to deflect with very old and a change of subject. But it's actually one of the most technically demanding questions in all of astrophysics. And the answer, when you finally get it, carries the weight of cosmic history. To understand how scientists age a star, you first have to understand what a star is doing in the first place. A star is a balancing act. It is an enormous ball of gas, mostly hydrogen, some helium, traces of heavier things, held together by its own gravity. Gravity wants everything to fall inward, wants to compress it all down into a single, impossibly dense point. And it would, if nothing pushed back. What pushes back is fusion. Deep in the core of a star, the pressure and temperature are so extreme that hydrogen atoms are forced together. They collide, they merge, and they become helium. In the process, they release energy, a staggering amount of energy. That energy radiates outward, pushing against gravity, holding the whole thing up. The star finds its balance, gravity pulling in, fusion pushing out, and it holds that balance for millions or billions of years. But hydrogen is a fuel, and fuel runs out. As the star burns through its hydrogen, the balance shifts. The core contracts, the outer layers expand, the surface cools, A star that was once burning bright and white grows redder, larger, slower. Eventually, depending on its mass, it swells into a red giant or collapses or explodes. But before all of that, before the drama, there is a long quiet period called the main sequence, the time when a star is simply burning, simply being, simply sustaining that ancient balance between gravity and fusion. How long a star spends on the main sequence depends almost entirely on one thing: its mass. A massive star burns through its fuel quickly, furiously, like someone throwing logs onto a bonfire. The bigger the fire, the faster it consumes everything. Massive stars might only last a few million years before they exhaust their fuel and collapse in spectacular supernovas. Brief lives by cosmic standards, brilliant and violent and gone. A smaller, dimmer, less energetic star burns its fuel slowly, carefully, like a single candle flame in a vast dark room. Low-mass stars, stars smaller than our Sun, can spend hundreds of billions of years on the main sequence, longer than the current age of the universe, which means the smallest, dimmest stars that formed in the early universe are, in a very real sense, still here, still burning, still balancing, unchanged in any way we could detect from a distance. Think about what that means. Somewhere in our galaxy, in many galaxies in fact, there are stars that have been burning continuously since the universe was less than 1 billion years old, stars that were already shining when the Milky Way was still a chaotic swarm of protogalactic fragments, slowly merging into a spiral, stars that predate not just every living thing, not just every rock on Earth, not just the Earth itself, but the Sun and the molecular cloud the Sun formed from, and the supernova that seeded that cloud with heavy elements. These stars exist. They are real. We can point telescopes at them. Methuselah is one of these stars, a low-mass, low-metallicity star. And that second word, metallicity, is the key that unlocks its age. Metallicity. It sounds like something from a music review, not astrophysics. But in cosmology it has a very specific meaning, and once you understand it, the age of the universe starts to feel like something you can almost hold in your hands. To astronomers, a metal is any element heavier than helium. Hydrogen, helium. Those are the light elements, the ones that existed from the very beginning, forged in the first few minutes after the Big Bang, in a process called Big Bang nucleosynthesis. Everything else, carbon, oxygen, iron, gold, uranium. Every element heavier than helium is a metal to an astronomer, and every one of those metals was made inside a star. Stars are the universe's foundries. They take hydrogen and helium and fuse them into heavier and heavier elements. They create carbon in their cores, oxygen, neon, magnesium. The most massive stars push the chain further: silicon, sulfur, calcium, iron. And when those massive stars finally die and explode, they scatter everything they made across space. That material becomes part of the molecular clouds that later collapse to form new stars, new systems, new planets, new worlds where, billions of years later, beings made of those same stellar remnants look up at the sky and wonder. This is why everything you are made of was once inside a star. The iron in your blood, the calcium in your bones, the carbon that forms every molecule in every cell of your body. All of it forged in stellar cores and scattered by stellar deaths across billions of years and billions of light years of space. But here is what matters for Methuselah. When the universe first formed stars, there were no metals. There couldn't be. The metals didn't exist yet. The first generation of stars formed from almost pure hydrogen and helium. They burned, they died, they seeded space with heavier elements. And then the second generation of stars formed from gas that was now slightly enriched, mostly hydrogen and helium but with traces of heavier things. Then those stars lived and died, and the third generation was even richer, and so on. Generation after generation of stars, each one forming from material slightly more enriched than the last. like a recipe that gets a little more complex every time someone adds to it. This means the metallicity of a star is a kind of fingerprint, a star with very low metallicity, one that formed from nearly pure hydrogen and helium, formed early, when the universe was young and the foundries hadn't been running long. A star with high metallicity formed later, from gas that had been recycled through many stellar generations. Our own Sun, for reference, has a metallicity that reflects its age. It formed 4.6 billion years ago from gas that had already been processed through several prior stellar generations. There is iron in the Sun that was forged inside a massive star that exploded before our solar system existed. There is oxygen that was built in the cores of stars that lived and died 1 billion years before the Earth formed. The Sun carries all of that history inside it, measurable in the proportions of elements we can read from its light. Think of metallicity as a timestamp, not a perfect one, not a precise calendar date stamped on the star at its formation, but a clear indication of how long the universe's foundries had been running before the gas that became this star ever collapsed. A low metallicity star is one that formed before many generations of stellar life and death had had time to happen. It formed early, from nearly pristine raw material. Its poverty of heavy elements is the direct record of a young universe. Methuselah has extremely low metallicity, vanishingly low. Its iron content is about 1/250th of the Sun's. That is not a rounding error. That is a statement of profound antiquity. It is, in the technical classification, a population 2 star, one of the oldest class of stars we can observe in our galaxy. It formed from gas that was almost untouched by stellar processing, almost primordial. This tells us it is old, very old in a way that connects it directly to the universe's earliest chapter. But knowing it is old is not the same as knowing how old. For that we need a more precise tool. The most reliable way to date a star is through a process called isochrone fitting. It sounds complex, and the mathematics underneath it genuinely is, but the concept is surprisingly elegant. When you plot stars on a graph, brightness on one axis, colour on the other, they don't scatter randomly. They fall into distinct patterns. The main sequence, that long diagonal band where hydrogen-burning stars live. The red giant branch, where older stars have expanded and cooled. The horizontal branch, the asymptotic giant branch. These patterns are not arbitrary. They are the inevitable result of stellar physics. The exact shape of these patterns depends on the age of the stars forming them. A young cluster of stars has a long, full main sequence. All the young stars still burning away, from the bright and massive down to the dim and small. An older cluster has had time to lose its most massive, fastest burning members. They have already died, already exploded, already ended, so the top of the main sequence is gone. The cluster's diagram shows a shorter main sequence, with a turn-off point where the remaining stars are beginning to evolve away from it. That turn-off point is the clock. The turn-off point in a stellar cluster tells you exactly how massive the stars are that are just now leaving the main sequence, just now reaching the end of their hydrogen supply. And from that mass you can calculate the age. The physics of stellar evolution is well understood. The relationship between mass and main sequence lifetime is reliable, so if you find the turn-off point, you find the age. For Methuselah, astronomers did exactly this. They looked at the star's position on the colour magnitude diagram. They modelled its interior structure. They accounted for its composition, its luminosity, its temperature. They ran the numbers, and the number they kept getting back was somewhere around 14 billion years, which is, to state the obvious, older than everything else we know of. The universe, according to our best cosmological measurements, is 13.8 billion years old. That number comes from multiple independent lines of evidence. The cosmic microwave background, the expansion rate of the universe, the distribution of galaxies across the sky. It is one of the most precisely measured numbers in all of science. We are confident in it. And Methuselah was coming back older. The first time this happened, it was easy to dismiss as measurement error. Stellar ages are hard to pin down. There are uncertainties everywhere, in the distance measurements, in the composition estimates, in the models themselves. A margin of error of 1 billion years or two is not unusual. Maybe the star was 12 billion years old, maybe 13. These things happen. But the measurements kept coming back high. And in 2013, a team led by astronomer Howard Bond published a careful, comprehensive new analysis using the Hubble Space Telescope. They updated the distance to the star using precise parallax measurements. They refined the composition estimates. They ran the most thorough analysis anyone had done. Their best estimate, 14.46 billion years, with a margin of error of plus or minus 0.8 billion years. The lower end of that range, 13.66 billion years, was just barely consistent with the age of the universe. Just barely. By the thinnest possible margin, Methuselah could fit. But the central value was still older, still impossible by the numbers, and the scientific world quietly held its breath. Let's pause here for a moment, because this is a good place to think about what it actually means when a measurement contradicts the established picture. What happens when a number comes back wrong? In popular culture, science is often portrayed as a fixed thing, a body of settled facts, handed down from textbooks, memorized by students, defended by experts. In this view, when something contradicts the established model, it is simply wrong. There is a right answer, and everything else is noise. But that is not how science actually works. Science is not a collection of facts, it is a process. And a central part of that process is exactly this. Moments of contradiction, of tension, of something that doesn't quite fit. A measurement that comes back wrong is not necessarily a mistake. It might be a signal. It might be the universe, in its patient way, trying to tell you something you haven't understood yet. The history of cosmology is full of these moments. In the 1990s, 2 teams of astronomers set out to measure the expansion rate of the universe using distant supernovas. They expected the expansion to be slowing down. Gravity should be pulling everything back together, decelerating the outward rush of galaxies. What they found instead was that the expansion was speeding up, accelerating, growing faster over time. This was, at the time, one of the most disorienting results in modern physics. It implied the existence of something, some energy embedded in the fabric of space itself, that was pushing the universe apart. Something with no clear physical explanation. They called it dark energy because they didn't know what it was. They still don't, not really. But the measurement was so clean, so consistent across 2 independent teams using different data, that the result had to be accepted. The model had to change. That discovery won the Nobel Prize, not because the scientists found what they were looking for, but because they found something that didn't fit, and followed it honestly to where it led. Every one of those contradictions, when taken seriously, led somewhere new. So when Methuselah came back older than the universe, the response from serious scientists was not panic, and it was not dismissal. It was careful, methodical attention. The question they asked was not what went wrong. It was, what are we missing? And behind that question was another, quieter one. The kind of question that doesn't appear in journal abstracts, but drives a lot of late nights in observation rooms and offices with too many coffee cups on the desk. Is this a mistake, or is this a discovery? Because those 2 things can look identical at first. A systematic error in your distance calibration looks exactly like evidence of a new physical process, until you figure out which one it is. A flaw in your stellar evolution models looks exactly like a genuine paradox in cosmology. Distinguishing between them requires patience and humility and willingness to spend years checking your assumptions one by one. The scientists who studied Methuselah did all of this. They checked the parallax and rechecked it, and then checked it again with a better telescope. They reanalyzed the spectra, updated the atomic physics, revised the models of stellar interiors. They considered every source of uncertainty they could identify. They were honest about what they found, which was, better measurements brought the age down, but not enough. The tension persisted. It was smaller than it had been, but it was still there. That kind of careful, self-critical honesty is science working exactly as it should. It is the opposite of the caricature, the defensive expert protecting their preferred answer. It is people with a genuine commitment to knowing the truth, following the evidence wherever it leads, even when it leads somewhere inconvenient. There are several places where the answer to the Methuselah problem could be hiding, and each of them opens a different door. The first place to look was the simplest, the star's distance. Stellar age estimates rely heavily on knowing how luminous a star is, how much light it is actually producing. But from Earth, we can't directly measure luminosity. We can only measure brightness, how much light reaches us. To convert brightness into luminosity, you need to know the distance. The farther away something is, the dimmer it appears. Get the distance wrong, and you get the luminosity wrong. Get the luminosity wrong, and your age estimate is off. In the early measurements of Methuselah's age, the distance estimates came from older parallax data, measurements taken from ground-based telescopes with all the limitations that entails. Parallax is the technique of measuring how much a star appears to shift against the background sky as Earth moves around the Sun. A nearby star shifts more, a distant star shifts less. The amount of shift tells you the distance. It is the same visual trick that lets your brain judge depth. Hold up one finger in front of your face and close each eye alternately. Your finger seems to jump back and forth against the background. That's parallax. Your two eyes are separated by a few centimeters, and the difference in viewing angle lets your brain triangulate the finger's distance. Astronomers do the same thing, but instead of two eyes separated by centimeters, they use two measurements separated by the diameter of Earth's orbit around the Sun, 300 million kilometers. The baseline is vastly larger, and still, for distant stars, the shift is almost unimaginably small. For a star as far away as HD 140283, about 190 light-years away, even this shift is tiny, a fraction of an arc-second. An arc-second is 1/3600th of a degree, and the parallax shift of Methuselah is a fraction of that. Measuring it precisely from the ground, through the blurring effects of Earth's atmosphere, is genuinely difficult. Any error in that measurement ripples through every calculation that follows. When Howard Bond's team used the Hubble Space Telescope to remeasure the parallax, they got a more precise distance, and a slightly different distance means a slightly different luminosity. A slightly different luminosity shifts the star's position on the colour magnitude diagram, and that shift changes the age estimate. The result of this more precise measurement was that the age came down slightly, from the extreme values of 16 billion years that earlier, cruder analyses had suggested, down to 14.46 billion. Progress, but not enough progress to resolve the tension. The Gaia Space Telescope, launched in 2013 and continuously refining its measurements since, has given us the most precise parallax data ever gathered for stars in our galaxy. Its measurements of Methuselah's distance have added further precision. Each new measurement has tightened the constraints. The current best value for the star's age is somewhere in the range of 13.7 to 14.3 billion years, depending on which models and parameters you use. Still old. Still right on the edge of, or slightly past, the age of the universe. Close enough that you might say, within error bars, we're fine, move along. But the error bars have gotten smaller, and the central value stubbornly refuses to fall below the universe's age on its own. So distance alone hasn't fully solved it. The second place to look was the star's composition. Metallicity affects the appearance of a star in ways that feed directly into age estimates. A star's spectrum, the specific pattern of light it emits and absorbs, is a fingerprint of its composition. Each element absorbs light at characteristic wavelengths, leaving dark lines in the spectrum. By analysing those lines, astronomers can determine what the star is made of, and in what proportions. For Methuselah, the iron content, the standard measure of metallicity, is about 1/250th of the Sun's, 1/250th. That is extraordinary. Our Sun, itself, a population 1 star of middling age, has been enriched by billions of years of previous stellar generations. Methuselah formed when almost none of that enrichment had happened. But composition measurements are not perfectly clean. There are systematic uncertainties in the atomic physics of spectral lines. There are assumptions built into the models about how elements are distributed through the star, whether the surface composition reflects the interior, whether mixing has occurred, whether certain processes have altered the apparent abundances over time. One element in particular attracted attention: oxygen. The ratio of oxygen to iron in a star like Methuselah is important because oxygen affects the opacity of the stellar atmosphere, how transparent or opaque the star's outer layers are to radiation. That opacity affects how we model the star's structure, and the structure model feeds directly into the age estimate. Change the assumed oxygen abundance by a modest amount, and the derived age shifts. In the early analyses, the oxygen to iron ratio was uncertain. When researchers refined this ratio with better measurements and more sophisticated atomic physics, the age estimate shifted. Not dramatically, but measurably. There is also the question of helium abundance. The proportion of helium in the star's core affects how the star evolves over time and therefore affects where it sits on the colour magnitude diagram at any given age. Helium is notoriously difficult to measure directly in cool stars like Methuselah. It simply doesn't produce strong spectral features in the visible wavelengths we observe most easily. So it must be inferred, estimated, modelled. Each inference carries its own uncertainty. This is the nature of these calculations. Each parameter feeds into the others. Change one input slightly, and the output shifts. The age estimate is not a simple number derived from a single measurement. It is the result of a complex interconnected web of physics, each piece dependent on the others. It is less like reading a single dial, and more like reconstructing what time it is by looking at shadows and inferring the sun's position from the lengths and angles. Accurate, but requiring careful accounting of every assumption. The frustrating and fascinating thing about Methuselah is that when you systematically go through each source of uncertainty and update it with better data, the age comes down, but not far enough, not consistently below the age of the universe. It's like a budget that won't quite balance no matter how many times you check the math. The third possibility is the most interesting, the most unsettling, the most quietly revolutionary. What if the problem isn't with the star? What if the problem is with our measurement of the universe? The age of the universe is derived from what cosmologists call the standard model of cosmology, lambda CDM, which stands for lambda cold dark matter. This model, built up over decades of observation and theory, describes the composition and evolution of the universe with remarkable precision. It tells us what fraction of the universe is ordinary matter, what fraction is dark matter, what fraction is dark energy. It tells us how fast the universe is expanding, and from those parameters, particularly the expansion rate, you can calculate the age. The expansion rate has a name, the Hubble constant. Named for Edwin Hubble, who first demonstrated that the universe was expanding in the 1920s, transforming our picture of the cosmos from something static and eternal into something dynamic and finite in time. The Hubble constant tells you how fast galaxies are moving away from each other per unit of distance. It's usually written as h0 with a subscript 0 to indicate it's the current value, because the expansion rate has changed over time, slower in some epochs, faster in others, shaped by the balance between gravity pulling matter together and dark energy pushing it apart. Here is the problem. The Hubble constant is currently at the centre of one of the most significant disputes in all of cosmology. Two completely different methods of measuring it keep giving different answers, and the difference matters enormously for the age of the universe. One method looks at the early universe, specifically the cosmic microwave background, the faint glow of radiation left over from the universe's first moments. About 380,000 years after the Big Bang, the universe cooled enough for hydrogen atoms to form. Before that moment, the universe was a plasma, a hot, dense soup of charged particles that scattered light constantly, like fog so thick that light couldn't travel through it. When neutral atoms formed, the fog cleared. Light was suddenly free to travel, and that light, carrying the imprint of every ripple and fluctuation in the young universe, has been travelling ever since. We see it today as a faint microwave glow coming equally from every direction in the sky, cooled by 13 billion years of expansion to just 2.7 degrees above absolute zero. It is the oldest light we can observe. The echo of creation. This relic radiation has been mapped in extraordinary detail by missions like the Planck satellite. The tiny temperature variations in the map, hotspots and cold spots differing by millionths of a degree, encode the physics of the early universe with astonishing precision. From those patterns, you can derive the Hubble constant. This method gives a value of roughly 67 to 68 kilometers per second per megaparsec. The other method looks at the late universe, measuring distances to nearby galaxies using a chain of overlapping distance indicators known as the cosmic distance ladder. Pulsating stars called Cephas variables, which brighten and dim in a regular cycle whose period is directly related to their intrinsic luminosity. Type 1. Supernovas, stellar explosions so consistent in their peak brightness that they can be used as standard candles across billions of light years. Surface brightness fluctuations in elliptical galaxies. This method consistently gives a higher number, roughly 73 kilometers per second per megaparsec. The difference between 67 and 73 might look small. It is not. It is enormous. The two measurements represent fundamentally different things about the universe's history. If the true value is lower, the universe is older and expanded more slowly. If the true value is higher, the universe is younger and expanded faster. If the Hubble constant is slightly higher than the Planck measurement suggests, if the true expansion rate is a bit faster, then the age of the universe would be somewhat younger than 13.8 billion years, maybe 13.4, maybe 13.0. And that would make the tension with Methuselah worse, not better. Conversely, if the Hubble constant is slightly lower, if the expansion has been slower, the universe could be older. 14 billion years. Maybe older. And that would dissolve the tension with Methuselah entirely. This dispute, known as the Hubble tension, has been one of the most discussed problems in cosmology for years now. It has not been resolved. The measurements from both sides have been checked, double-checked, improved with better data, cross-validated with new methods. New distance indicators have been brought in to check the distance ladder's calibration. The early universe measurements have been re-examined for systematic biases. New analysis techniques have been applied. The discrepancy hasn't gone away. It has, if anything, grown more solid as the error bars have tightened on both sides. The measurements are not converging. They are stubbornly pointing in different directions, which means either there is a systematic error in one or both methods, some subtle flaw in the measurement chain that nobody has identified yet, or there is something genuinely wrong with the standard model, something missing from the picture. Some piece of the universe's story that we haven't accounted for, and the existence of Methuselah, this single ancient inconvenient star, sits at the intersection of all of it. There is something almost poetic about what Methuselah is doing to our cosmology. We built our model of the universe from the top down and from the bottom up simultaneously. From the bottom up, we looked at individual stars, measured their ages, built our understanding of stellar physics one observation at a time. From the top down, we measured the expansion of the universe, mapped the cosmic microwave background, derive the age and composition of everything from the patterns in the oldest light we can see. These two approaches were always supposed to agree. The universe should be self-consistent. The age you derive from stellar physics should match the age you derive from cosmology. The oldest stars should be younger than the universe they formed in. And for a while, roughly, they did. There were always some discrepancies, always some tension, but nothing irreconcilable. The error bars overlapped. The stories matched more or less. Then Methuselah kept coming back too old, and the Hubble tension emerged, refusing to go away, and two cracks appeared in the picture, not fully reconciled, stubbornly persistent. It is tempting to say that these cracks mean nothing, that they will be filled in by better measurements, better models, incremental improvements to existing techniques, and they might be. The history of science is full of apparent contradictions that dissolved once someone found the right measurement, the hidden systematic error, the overlooked calibration factor. But it's equally possible that they mean something, that the universe is trying to tell us something we haven't quite heard yet, that the model we've built, elegant and precise and extraordinarily well tested as it is missing something fundamental, not dramatically wrong, not thrown out wholesale, but subtly incomplete, like a map that's mostly right, but with a region in the corner where the coastline doesn't quite line up. Let's come back to the star itself for a moment, because in all this talk of models and tensions and error bars, it's easy to forget that Methuselah is a real object, real in a way that numbers on a page are not. It is out there, right now, burning, not far from us by cosmic standards, 190 light-years away, a modest distance, a star you can see, if you know where to look, in the constellation Libra, not visible to the naked eye, but reachable with a modest telescope. A small, dim point of light, unremarkable in appearance. And yet, it formed when the universe was less than 1 billion years old, when the cosmos was still young and chaotic, still finding its structure, when the first stars of the universe were just beginning to live and die, seeding space with the first metals, when galaxies were still assembling themselves from the primordial fog. Methuselah was there. It formed from a cloud of gas that was almost entirely hydrogen and helium, gas that had never been inside a star, gas that was, in some sense, as close to the original material of creation as anything we can study. It condensed and collapsed and ignited and has been burning slowly, steadily, without drama, ever since. While stars around it formed and died, while the Milky Way assembled itself over billions of years, spiral arms taking shape, the central bar solidifying, generations of stars living and ending in the disk around it. While our own sun formed, 4.6 billion years ago, from a cloud of gas already richly seeded by previous stellar generations, while the planets formed around our sun, while life appeared on one of those planets, crawled out of the oceans, stood upright, looked up. While all of that happened, Methuselah burned. It has been in the outer halo of the Milky Way, away from the busy disk, away from the churning spiral arms, moving in a long, slow orbit. Its orbit is highly eccentric, which is itself a clue to its history. It swoops in toward the galactic centre, and out again over the course of hundreds of millions of years, tracing a path that takes it through very different environments. When it passes through the inner galaxy, it moves through denser regions. When it retreats to the outer halo, it moves through the thin, quiet spaces where very little happens and time seems to pass differently. The stars in the disk orbit more or less in the same plane, in the same direction, like a slow carousel. Methuselah doesn't. It moves at a steep angle to the disk, a relic of a time before the galaxy had fully settled into its current shape, before the various smaller galaxies and star clusters that merged to form the Milky Way had fully dissolved into the larger whole. It is, in a very real sense, not quite of our galaxy, or rather, it is from a time before our galaxy was what it is now. It remembers a different universe. And that detail, the orbit, is another way astronomers have constrained its age. The orbital dynamics of a star like Methuselah, combined with what we know about the assembly history of the Milky Way, are consistent with it being among the oldest stars we will ever find in our cosmic neighbourhood. There are older things in principle, galaxies in the distant universe, observed as they were billions of years ago, already containing ancient stars, but those are remote, abstract, observable only as collective smudges of light, their individual stars impossible to resolve and study. Methuselah is nearby, real, a stone's throw, cosmically speaking. It is the oldest thing we can actually study in any detail. There is a question that scientists have been quietly turning over for years now. It doesn't appear often in press releases because it sounds too much like science fiction, and press officers are careful people. But in conference rooms and seminar halls and the occasional late-night discussion over cooling coffee, it gets asked. What if there were stars before our universe? Not in our universe, before it. Before the Big Bang, if before is even a meaningful concept. In some prior state of existence. There are cosmological models, legitimate, peer-reviewed, seriously considered models, in which our Big Bang was not the beginning of everything, but merely the beginning of our particular chapter. Cyclic cosmologies, in which the universe expands and then contracts and then expands again in an endless cycle, each expansion a new Big Bang. Or eternal inflation, in which our universe is one bubble in a vast, possibly infinite sea of expanding space, each bubble a different universe, with different physical parameters. In some of these models there is no absolute beginning. There is no moment of true creation. There are instead transitions, previous states collapsing or bouncing or tunnelling into new ones, new Big Bangs igniting in the quantum foam, new universes bubbling into existence with new physics, new constants, new histories. If any version of this is true, then a star being older than our Big Bang is not logically impossible. It would require some mechanism for surviving the transition, which is admittedly hard to imagine given what transitions between cosmic epochs imply. The temperatures and densities involved in a Big Bang or in a cosmological bounce would seem to preclude the survival of anything as delicate as a star. But the theoretical space is at least not empty. The door is cracked open, if only just. These models are not the mainstream. They are speculative, difficult to test, easy to caricature. And Methuselah does not require them. As we have seen, there are conventional explanations that can almost account for its age. Almost. But the possibility exists, and the fact that it exists at all, that serious physicists can sketch out scenarios in which something could predate our Big Bang, is itself a reminder of how strange and how open the deepest questions still are. Let's talk about measurement uncertainty more carefully, because it's central to everything here, and it's a concept that is genuinely easy to misunderstand. When a scientist reports a measurement with an uncertainty, when they say the age of Methuselah is 14.46 plus or minus 0.8 billion years, they are not saying they made a mistake. They are not saying they don't know the answer. They are communicating something precise and important. This is the range within which we are confident the true value lies, given the data we have and the models we used. The uncertainty is not a flaw. It is information. It tells you the quality of the measurement. It tells you how much the answer might shift if you refine the technique, gather more data, improve the models. But here is the thing about uncertainty that is easy to forget. It does not mean the true value is equally likely to be anywhere in that range. Uncertainties in science are typically expressed as standard deviations, meaning the true value is most likely to be near the centre and increasingly unlikely to be near the edges. The probability distribution is shaped like a bell curve. The reported number is the peak of the bell. The uncertainty tells you how wide the bell is. So when Methuselah comes back at 14.46 billion years with an uncertainty of 0.8 billion, the most likely age is still 14.46 billion, older than the universe's best fit age of 13.8 billion. The lower end of the error bar, 13.66 billion, is possible, but it is less likely than the central value. This is why the tension hasn't simply been waved away. The overlap at the edges of the error bars is real, but it requires both measurements, the star's age and the universe's age, to simultaneously be at the ends of their respective distributions that are most favourable for consistency. Both measurements landing at their most convenient possible values at the same time. That happens sometimes, but it would be a coincidence. More than that, as the error bars shrink with better data, if the central values don't move toward each other, the overlap disappears entirely. The tension becomes a genuine contradiction, and over the years, as measurements have improved, the tension has shown no strong tendency to dissolve. So far, the age estimates are getting tighter, and they are getting closer to consistency, but not fully there. Not yet. The numbers are in conversation with each other, circling toward agreement without quite arriving, and every new telescope, every new data set, every new model refinement tips the scale slightly one way or another. Here is something worth sitting with for a moment. We are attempting to measure the age of a single star to within 100 million years. 100 million years. That sounds like a lot. 100 million years is an almost unfathomable span of time. It is more than twice the length of time that dinosaurs existed on this planet. It is long enough for entire mountain ranges to rise and erode and be replaced by new ones. It is long enough for the entire recorded history of human civilization to repeat itself 10,000 times over. And yet, in the context of cosmic time, 100 million years is the level of precision we are demanding. It is the difference between a result that is consistent with cosmology and one that breaks it. We need to know the age of a star 190 light-years away, a point of light whose internal structure we cannot directly observe, whose composition we infer from patterns of light, whose luminosity we calculate from its brightness and a distance, measured by the wobble of starlight across the sky, to within 1% of its total age. This is not a critique. It is an act of genuine awe. The fact that we can do this at all is extraordinary. The fact that we can look at a point of light in the sky and say, with any confidence at all, that it formed 14 billion years ago, that it was there when the universe was less than 1 billion years old, is one of the most remarkable things human beings have ever accomplished. It required centuries of accumulated physics. It required understanding of quantum mechanics and nuclear physics and radiative transfer, the way light moves through gas. It required space telescopes and spectrographs and massive computational models running on machines that didn't exist a generation ago. It required generations of astronomers, each building on the work of those before, each adding one more brick to the edifice. It required the long, patient accumulation of knowledge that is science at its finest, and it resulted in a number that doesn't quite fit, a number that sits at the edge of the possible, just barely inside the allowed range, or maybe just outside it, depending on which measurements you trust most and how you weight the uncertainties. A number that keeps everyone honest. There is a phrase in science, the universe doesn't care what we think is tidy. It means that nature has no obligation to make itself simple, or consistent with our intuitions, or easy to measure. It is what it is. Our models are approximations of it, not the other way around. And our job, the job of science, is to figure out what it is, not to persuade it to be something more convenient. Methuselah is not convenient. It does not make cosmology easier. It does not simplify the picture. It arrives in our data carrying an impossible number and declines to explain itself, but it makes the picture richer. It is a reminder that our models, however good, are approximations, that every number in the cosmological standard model is a best current estimate, not a final truth, that the error bars are not decorations, they are invitations, invitations to do better, to measure more carefully, to question the assumptions that seemed most solid. The Hubble tension, Methuselah's age, the puzzling distribution of the oldest stars in the Milky Way's halo, these are not embarrassments to be quietly swept aside. They are data, and data, even inconvenient data, especially inconvenient data, is where progress lives. Some of these tensions will likely dissolve with better measurements, better parallax from future astrometric missions, better spectroscopy from the next generation of extremely large telescopes being built right now on mountaintops in Chile and Hawaii, better models of stellar structure incorporating updated nuclear reaction rates from particle physics experiments. These improvements are coming. They are in progress. The numbers will tighten further. And when they do, either the tension will vanish, and we will breathe the kind of relieved breath that comes from a problem solved, or it won't. And if it won't, then something genuinely new is waiting to be found. Something that changes how we understand the history of everything. Either outcome is good, either outcome is science working as it should. There is one more thing worth saying about this star. Something beyond the measurements and the models and the tensions. It is about time. We talk about the age of the universe, 13.8 billion years, as if that number were a simple fact, easy to hold, clear in meaning. But 13.8 billion years is a number so large that it evades all human comprehension. We can write it down. We can use it in equations. We cannot feel it. We cannot stand at one end of it and look toward the other. What we can do is look at Methuselah. This star formed when the universe was perhaps 600 million to 800 million years old, which means it has been burning continuously, without pause, without interruption, for roughly 13 billion years. It watched, in the only way a star can watch, as the universe assembled itself around it, as galaxies formed and merged and collided and reformed, as the Milky Way took shape from the chaos of smaller protogalaxies, as our solar system condensed from a cloud of stellar debris 9 billion years into Methuselah's life, as all of Earth's geology happened, the continents forming and drifting, mountains rising and eroding, the ice ages coming and going, as life appeared, diversified, discovered fire, invented writing, built telescopes and pointed them at the sky. All of that happened after Methuselah was already old, already billions of years into its long, quiet life. There is a way of holding this fact that can feel vertiginous. You reach for a comparison that might make it tangible. You want an analogy, something to stand beside the number and make it feel real. And nothing quite works. If the entire history of the Earth were compressed into a single calendar year, Methuselah would have been burning for 3.5 years before that calendar even started. 3.5 years during which there was no Earth, no sun, no solar system of any kind, just that ancient star, burning in the dark in a universe still assembling itself, and it is still burning. Right now. Tonight, as you listen to this. That same ancient star running the same slow nuclear fire, holding the same balance between gravity and fusion that it has held since a time we cannot fully imagine. 190 light-years away, which means the light reaching your eye tonight, if you were to find it with a telescope, to seek out that faint point of light in Libra, that light left Methuselah 190 years ago. It crossed the void while empires rose and fell here, while the Industrial Revolution reshaped the human world, while Darwin wrote and Beethoven composed, and the first photographs were being taken, and trains crossed new continents, and entire nations were born and died. That light is old too by human standards, but it is nothing, a blink, a whisper, compared to the star that made it. So what do we do with this? With a star that should not exist, that possibly, just possibly at the edge of measurement and model, is older than the universe that contains it. We do what scientists always do. We keep looking. We measure again, more carefully this time. We build better tools. We question the assumptions that seemed most solid. We hold the tension without collapsing it prematurely into a comfortable resolution. And we let it do what uncomfortable facts always do to knowledge. Push it forward. It is worth noting that this is not the first time cosmology has faced a crisis of ages. In the early 1990s, before the full precision of modern measurements was available, there was a period when the best estimates of the universe's age were embarrassingly close to, or younger than, the ages of the oldest globular clusters, which are dense balls of ancient stars bound together by gravity and scattered through the halo of our galaxy. The clusters kept coming back older than the universe by hundreds of millions of years, sometimes more. It was a genuine, widely discussed problem. Then better measurements of the Hubble constant combined with the discovery of dark energy and its effect on the universe's expansion history resolved the tension. The universe's age was revised upward. The models were improved. Everything fit more or less. That resolution happened because people took the discrepancy seriously, because they measured again and again and built better models and were willing to accept a result: dark energy, the accelerating expansion that was deeply counterintuitive. The discomfort was productive. The tension led somewhere real. Methuselah might follow the same path. The tension might dissolve cleanly as measurements improve and models are refined. Or it might deepen into something that genuinely requires new physics, a modification to our understanding of how the universe expanded or how stars age, or both. We do not yet know which it will be. There will come a time, perhaps in this generation, perhaps in the next, when the combination of better measurements from Gaia and its successors, better stellar models from computational astrophysics, and better cosmological constraints from surveys of the early universe will either solve the Methuselah problem definitively or deepen it into something genuinely revolutionary. Either way, the story is not over. In the meantime, the star burns, patient and ancient and indifferent to our equations. It has been burning since before there were stars in this part of the sky. It will likely burn for billions of years more. Low-mass stars are slow to age, slow to die. By the time Methuselah finally exhausts its hydrogen and begins to swell into a red giant, our own sun will have already done the same and taken the inner planets with it. Methuselah will outlast us by so much that the number doesn't fit in any analogy I could construct without breaking it. And during all of that remaining time, during the billions of years Methuselah will continue burning after we are gone. It will simply be there, a point of light in whatever sky exists then, a relic of the first chapter of the universe's story, still going, still sustaining that ancient balance, witnessed by no one in particular, or perhaps by minds we can't yet imagine. It asks nothing of us. It requires no audience. It was burning before anything in this solar system existed, and it will burn long after everything here has ended. We are, in a sense, the newcomers here. Our sun is a child compared to this star, the Earth, our civilization, our entire accumulated span of existence from the first campfire to the last line of code. All of it is a brief flicker against the timescale of Methuselah's life. That thought could be humbling in a diminishing way. You might feel small in the face of it, temporary, inconsequential. But I think it's something else entirely. I think it is an invitation to wonder. Because this star exists, and it is real, and we found it, and we measured it, and we pointed our best instruments at it and read the secrets encoded in its light. We, beings who live for perhaps 80 years on a pale blue dot orbiting a middle-aged star in a middling galaxy in one corner of a vast and ancient cosmos, we figured out how old it is. We knew, from patterns in light, from equations scratched on paper and solved in supercomputers, from data gathered by telescopes floating in space, that this particular dim and unremarkable star was burning before our galaxy was fully formed. That is what intelligence does, when it gets enough time and asks the right questions. And there is something profoundly moving about the fact that the oldest thing we can study is also one of the closest. We didn't have to look to the edge of the observable universe, billions of light years away, to find a relic of the earliest cosmic times. We found one in our own backyard, practically, a neighbour by astronomical reckoning, visible in a modest telescope from your own garden, in the same sky that every human being who ever lived has looked up at. Methuselah is not a distant abstraction. It is a local object. The light that left it 190 years ago is the same kind of light that left our sun 8 minutes ago. Photons carrying information across empty space, falling into lenses and mirrors and detectors and ultimately into the equations of patient human beings, trying to understand what everything is made of and how long everything has been here. The ancient and the nearby, existing in the same sky. The oldest thing we can study, hiding in plain sight. And the universe, which does not notice us, which does not care about our confusion, which does not calibrate its facts to our comfort. The universe left us a star to find. An ancient, dim, inconvenient star. Just sitting there in Libra, 190 light-years away, patiently waiting to be measured. Older, by some accounts, than time itself. Tonight, when you close your eyes, the sky above you is full of stars. Most of them are ordinary. Most are young by cosmic standards, formed from gas already enriched by many generations of predecessors. They burn brightly and will end dramatically, and are beautiful in all the ways that brightness and drama can be beautiful. But in the constellation Libra, a little south of the celestial equator, there is a star you cannot see without a telescope. Dim, quiet, unremarkable to the naked eye. It does not flash, it does not pulse, it does not announce itself. It has been burning since the universe was young. It carries in its light, encoded in the gaps in its spectrum, the record of a time before our solar system existed. Before our galaxy was what it is, before anything we know about life or Earth or human thought had begun. It is older than everything except the universe itself. Maybe, just barely maybe, older than that. And it is out there right now, in the dark above you, burning the same slow fire it has always burned, holding itself together with the same ancient balance, patient and enormous and radiating its faint red light across 190 years of empty space into the instruments of scientists who are still trying to understand it, still measuring, still refining, still asking, still looking up. Let the questions you can't answer yet carry you to sleep. The universe is old and strange and full of things that shouldn't exist. Most of them do anyway. That's what makes it worth looking at. Good night.